Welcome. Today we will be discussing section 5.3. Topics include de Moivre's theorem, unimodular numbers, roots of unity, and general root theorem. For de Moivre's formula, we have r times the quantity cosine theta plus I sine theta, and we're going to raise the entirety of this to the nth power, where n is a positive integer. The result of this is we get r to the n times the quantity cosine of n theta plus I sine n theta. Now, through the properties, we can see that we can distribute this n to raise this expression to the nth power and then raise r to the nth power. So really what we're looking at here is that cosine of theta plus I sine theta, this expression raised to the nth power results in cosine of n theta plus I sine of n theta. That is the crux of this formula, and we'll further define this with unimodular numbers. But let's first work with an example of using the Moivre's formula. So if we have 1 minus I and raise it to the 10th power, we might be interested into simplifying this expression. Well, I don't want to write out a binomial 10 times and distribute it. So instead, what I'll do is use de Moivre's formula. So we have to get it into this form. Well, this form isn't random. It is the polar representation of complex numbers. So that's what we're going to first do. We want to write 1 minus I in polar form. So we'll have to find our r, which is equal to the square root of 1 squared plus negative 1 squared. And that's our a is 1 and our b, the coefficient of I, is negative 1. So that results in just square root 2. We're taking just the principal root, so it'll be positive square root 2. We are not interested in a negative radius or r. And then our theta principal is equal to the sine of our b, which is negative, times cosine inverse of our a value, 1, divided by our radius, or r, which is square root 2. This 1 over root 2 is same as square root 2 over 2. Cosine inverse of square root 2 over 2 is pi over 4. We have a negative, so we're going to have negative pi over 4. This means when we rewrite 1 minus I, we have 1 minus I is equal to square root 2 times cosine of negative pi over 4. And then we're going to add I sine of negative pi over 4. And that is the polar representation of 1 minus I. So we're going to raise this to the 10th power. So we can rewrite this expression as square root 2 times cosine of theta, our theta is negative pi over 4 plus I times sine of negative pi over 4. And we're going to raise this to the 10th power, which I can rewrite this as square root 2 to the 10th times cosine of 10 times negative pi over 4 plus I times sine of 10 times negative pi over 4. And that is because of de Moivre's theorem. So root 2 to the 10th power, that's same as 2 to the 5th power. So that is 32. For cosine, we can simplify this angle to being negative 5 pi over 2 plus I times sine of negative 5 pi over 2. And we can think of the unit circle. We could also think of this being an even function. So we have 5 pi over 2, whichever is an easier way of trying to calculate it. We will determine that cosine of negative 5 pi over 2 is equal to 0. So we'll have 32 times something here, I times whatever sine of negative 5 pi over 2 is, which is negative 1. So we end up getting 32 times I and put negative in front. So the expression 1 minus I all raised to the 10th power is equal to negative 32I. So we'll now talk about unimodular numbers and some identities that we can utilize. So unimodular number identities. So we're going to let u be equal to cosine of t plus I sine of t, which then the properties that we have are u to the n for some positive power n, we get de Moivre's formula shows us you have cosine of nt plus I times sine of nt. So it's a simplification of what de Moivre's formula is. Now we can look at this and say, what if we're only interested in cosine of nt? What if we're only interested in sine of nt? Well, when we work through it, we end up finding that cosine of nt is equal to 1/2 times u to the n plus u to the negative n. We also get that sine of nt is equal to 1/2, or I should say 1 over 2i times u to the n minus u to the negative n. And for your check on learning, I want you to write down the unimodular identities. I want you to write down these identities for your check on learning. Where this is useful is when it comes to Fourier transforms. So let's see an example where we utilize the unimodular identities. So say if I gave you a function, and that function was f of t is equal to 4 times cosine t times cosine of 2t times sine of 3t. Well, we can rewrite cosine t, cosine of 2t, sine 2t in terms of this u. So we have 4 times For the cosine of t, this has a 1 in front for a coefficient. So when we plug it into the formula of cosine of 1 times t, we'll get 1/2 times u to the first plus u to the negative first. Let's record that here, 1/2 times u to the first, so I'm just gonna have u plus u to the negative first. And now we're going to do the same with cosine of 2t, which gives us 1/2 times u squared plus u to the negative seconds. Now we're going to times this, but we have sine, so we're going to have 1/2i times u to the third minus u to the negative 3. So we can simplify and go 1/2, 1/2 cancels out with a fourth. So we're left with 1/2i times by u plus u to the negative first times u squared plus u to the negative 2 times u to the third minus u to the negative third. And so now we can distribute. And when we distribute here, we'll get 1/2i still. Distributing, we have u to the third plus u to the negative first plus u to the first plus u to the negative third. And this is all times by u cubed minus u to the negative third. So we're going to distribute into the binomial. And this will yield f of t to equal 1/2i times, and we have u to the sixth minus u to the negative sixth. All right. No, just minus 1. So yeah, u to the sixth minus 1 plus u to u squared minus u to the negative fourth plus u to the fourth minus u to the negative second, and then plus 1 minus u to the negative sixth. So our ones cancel. And now we can group these and get u to the sixth minus u to the negative sixth. That's the grouping that we want to have. And then we can have the u to the fourth minus u to the negative fourth. And finally, we have the grouping of u squared minus u to the negative second. And we can work backwards. And we can distribute this to every single one of these, which now we're in, they'll all look like this, of 1/2i times u to some number minus u to the negative of that number. So for this first one, we'll have sine of 6t. We're going to add sine of 4t plus sine of 2t. And this is our f of x, or f of t, I should say. And now we can say that this is a Fourier function of order 6. So we have sine to the 6th. So I skipped the step of distributing this 1 over 2i to each grouping, but you can show that step, and it should be easy to see that this quantity reduces to sine of 6t, sine of 4t, and sine of 2t. Okay. So why do we care about this? Well, we want to find the roots of unity for problems. But let's first talk about what a root of unity is. So first, talk about roots. And we want to let x to some number n is equal to omega. And omega is generally fixed and often is known. We know exactly what number we're trying to reach here. And it's going to be a complex number. So where omega is complex. The solutions are called the nth roots of unity. So the nth roots of unity are the solutions to this equation. Or let me write this as star. And this is when n is greater than or equal to 2. So what happens is we are guaranteed that there are exactly n distinct roots of unity. Meaning I'm going to have n unique solutions, unique ways of writing x that result in omega. And we'll typically write them out as like u0, u1, u2, all the way to u to n minus 1. And we'll write that any such root of unity is equal to cosine of 2 pi over n and times it by whatever particular root that we're interested in, plus I sine of 2 pi over n times by the k. And again, this is where k is any root of unity that we're interested in. So we can define that as 0 less than or equal to k, less than or equal to n minus 1. And k is an integer. So whatever root that we're interested in, we can find it with this formula. So let's find the cubic roots of unity. So let's have x cubed is equal to, I'm going to rewrite this as z. Z cubed is equal to 1. We want to find all the roots of unity. So we apply this formula, and we're going to have u0 equals cosine of 2 pi to the n times 0 plus I times sine of 2 pi to the n times 0. Again, I'm having this formula. I've plugged in my k because I want the 0. What is my n? My n is a 3. So let me plug that in for my n. And now I have cosine of 0, that is 1, plus I times the sine of 0, which is 0. So this is just 1. That's u naught. One could guess that every u naught would equal 1, and that holds because we have our z cubed equaling 1, and it makes sense that 1 would equal 1. That's a way to write down 1. So it's a funny answer, but it's accounted for, and that's important. So now u1 equals, we have cosine of 2 pi over 3 times 1 plus I sine of 2 pi over 3 times 1. I'm omitting that because we can simplify. And now we think of that cosine of square root 2 pi, or sorry, cosine of 2 pi over 3, that is lost in my notes. Negative 1/2 plus, and here sine of 2 pi over 3 is square root 3 over 2. And we attach an I. So here's u1, here's our u0, and now we just need a u2. So u2 is equal to, and we have cosine of 2 pi over 3 times 2. So that is 4 pi over 3 plus I sine of 4 pi over 3. Evaluate these, and we get u squared is equal to negative 1/2 minus square root 2 over 3i. And those are our 3 roots of unity for z cubed. We know that there's no more because if I had like a u3, well, what would that essentially do? It'd make it 2 pi, which it's no longer distinct. It's now cosine 2 pi is the same as cosine of 0, and that's 0. So we're, or sorry, 1. So we're getting right back into u0. So we found all the distinct roots of unity. So let's take a look at the quadratic now. So we have z to the 4th is equal to 1. So when we look at the quadratic, we're going to do much of the same thing, where u0 is going to equal cosine of 2 pi over 4, because that's our power, and we're going to times it by which root we're interested in this case, 0, plus I sine of 2 pi over 4 times 0. And now, when we evaluate this, we again get u0 is equal to cosine of 0, which is 1, plus I sine of 0, which is 0. So we have u0 equals 1. Again, makes sense. We should get this because 1's a valid solution. 1 to the 4th is 1. So now we can look for u1, which equals cosine of 2 pi over 4, or that's same as pi over 2, plus I sine of 2 pi over 4 times 1, which is same as pi over 2. Check. And we can evaluate, and we get u1 is equal to cosine of pi over 2, that's 0, that goes away. Sine of pi over 2, that's 1, so we just get I. Which should also make sense because in the previous video, we had I to the 4th was equal to 1. So now we can look for u2, and we now have cosine of, we're going to have 2 pi over 4 times 2, so that's just pi, plus I sine of, again, just pi. Cosine of pi is -1. And I sine pi is 0, so we're left with u2 equals -1, which again we can plug in, and it makes sense intuitively. So now we have u cubed, and I think you could guess what this could be. And if you guess -I, you'd be correct. And if we think about that, we can split -I into I and -1, distribute the 4. -1 to the 4th is 1. I to the 4th is 1. So therefore we must have 1. But let's go through the formula. We'll have cosine of, now we have 2 pi over 4 times 3. So that will be 6 pi over 4, which is 3 pi over 2, plus I times 3 pi over 2, or it's the sine, I times the sine of 3 pi over 2. And now cosine of 3 pi over 2 is 0, sine of 3 pi over 2 is -1, so that leaves u3 equal to I, because we're going to have -1 times I. And again, if you try to go u to the 4th or sorry, u4, u5, we're not getting distinct values anymore, because if we plug in 4, we'll then have 2 pi, which is 0. If we plug in 5, we then get 10 pi over 4, which reduces to the same as cosine of 2 pi over 4, or pi over 2, and we get the same value. We no longer have distinct roots. So we can now generalize this. So what we can do is have general root theorem. And that is, let z to the n equal sub omega for omega not equal to 0. So we're fixing omega, and we just can't make it 0, otherwise it becomes pretty trivial. It doesn't matter. Well, then we have that there are exactly n distinct roots of unity or roots of w if w is not 1. And so let's do the exact roots of w, or omega, I should say. Z equals the nth root of omega, taking the modulus of omega. So the nth root of the modulus of omega times cosine of theta plus 2 pi k all over n plus I sine of theta plus 2 pi k all over n, where 0 is less than or equal to k, less than or equal to n minus 1. So what this is essentially doing is, before when we had it a root of unity, which is the z to the n equals 1, we didn't have a front term, and we would just had this 2 pi k all over n. We didn't have this theta. And what we're accommodating now is we can get the magnitude or the modulus of omega, and by taking the nth root, we're now solving that that z to the n would cancel out this nth root, and we'll get this same modulus. So we're going the same distance. It's not just 1 anymore. And then this theta accounts for us starting at any point along a circle, and then we're traveling a distance around the circle that is determined by what the root is and what the power that we're looking for. So you can think of this as, if we have a circle, the radius is the magnitude of omega to the 1 over n. And that's to account for what this and z to the nth power. And then we're going to start at some point, and then we're just going to rotate a certain distance. And once we rotate, in this case, I put up a quarter turn, there's only 4 possible solutions that we can get, and this would be symbolic of z to the 4th power, and we're going to start at some arbitrary angle of theta. So Let's see an example of how to use this. So we want to again find the cube roots of this time omega and not of unity. So we want to find cube roots of omega equals negative 8i. So we first want to find modulus of omega, which is the square root of 0 squared plus negative 8 squared, which equals 64 square root, which is just 8. And now for our z naught, we want to start off with the cubic root of 8, and we want to times by the cosine of some theta plus 2 pi times 0 all over 3. And we want to add I sine of theta plus 2 pi times 0 all over 3. So that's our z naught. And now let's do z1 equals, again, the cubic root of 8 times cosine of theta plus 2 pi times 1 all over 3 plus I sine of theta plus 2 pi times 1 all over 3. And our third one is so z2 is equal to cubic root of 8 times cosine of theta plus 2 pi times 2 all over 3 plus I sine of theta plus 2 pi times 2 all over 3. Now, what we want to do is we have these generalized, but now we want to pick a starting point. So if I choose theta to be negative pi over 2, we can now simplify all of these. So let's start with z0. So z0 is equal to, and now let's plug in pi over 2. Well, this goes away, this goes away. So we're left with theta divided by 3, which is just pi over 6. So negative pi over 6. So we're going to keep track of that. So let's have theta equal negative pi over 2. So we have cosine of negative pi over 6, which is square root 3 over 2, plus I times the sine of negative pi over 6, which is negative 1/2, And we can't forget about the cubic root of 8, which is 2. So we end up getting that z naught equals, and we have square root 3 minus I. So let's look at z1 now. We'll again have the same radius. We now plug in square our negative pi over 2 for theta, and we can then have this simplified into cosine of pi over 2, because we'll have 2 pi plus negative pi over 2, divide that all by 3. We end up getting cosine of pi over 2, which is 0, plus sine of pi over 2, which is 1. So we're going to get just 1 times I. And this z is equal to 2I. Or z1 is equal to 2I. And now when I look at z3, we have 2 times, and we'll have, we plug in negative pi over 2 in for theta. Solving, we get cosine of 7 pi over 6, which is negative square root 3 over 2 plus I times sine of 7 pi over 6, which is negative 1/2. Distribute the 2, and we get z3 is equal to negative square root 3 minus I. So again, what we're doing with this is we essentially have a radius, and when we started with the theta, we started at a particular point. So we started in this case at square root 3 minus I. So that would be somewhere about here. And when we went around the circle, it's right here. Because when we went around the circle, we go a third away around the circle. That gets us at the top, which is 2I. And then we come back a third away around the circle, gets us somewhere about there. And so we now split this circle into thirds. And those are 3 distinct roots of omega. So now we'll do one more example, and this time we'll solve a function. So let's have x to the 8th plus 15 x to the 4th minus 16 equals 0. And we want to solve all solutions. So what we can do is let omega equal x to the 4th. Because then, when we have that, we can now substitute in for omega, and we get omega squared plus 15 omega minus 16 equals 0. So we have omega plus 16 times omega minus 1 is equal to 0. So we have omega equals 16 or omega equals 1. Let me write that in the other order. Omega equals 1 or omega equals negative 16. Yeah, that's a better way. Because now, if omega equals 1, we substitute back in for x, so we have x squared, or sorry, x to the fourth is equal to 1. And this is the same as the quadratic roots of unity. So we can, so from the previous example, we have x naught is equal to 1, x1 is equal to I, x2 is equal to negative 1, x3 is equal to negative I. Because although I wrote an x, this x is a complex number. So we have to get used to thinking in the complex sense, which we could have found that x equals positive 1, negative 1, because those are real numbers, but we have to also imagine the complex, and we can plug this in the formula or from the previous exercise in the class. In this lecture video, we have already found those roots of unity. So now with 16, or negative 16, I should say, we have a slightly different case. Because now we have this being x to the fourth. We're finding the fourth root of negative 16. So we have x naught equaling the fourth root of the modulus of 16. Now note, this is the modulus of 16, not the absolute value of 16. However, it does mean the same thing in this instance. So we just have positive 16 and we take the fourth root of it. Times by cosine. And in this case, we're going to just keep the theta equaling 0. So we'll have actually, let me see. Theta plus 2 pi times our k, which is 0, all over n. Plus I sine of theta plus 2 pi times 0 all over n, which our n is 4, so let me just write that here. And so now I do not want to have theta equaling 0, because if I do, I'm going to have a trivial root. Instead, what I want to do is let's have theta equal something easy. So let's do pi. So if I do pi, we have x naught equaling, this will reduce down to 16 is just 2 to the fourth, so this is just 2 times cosine of pi over 4. Well, that is root 2 over 2 plus I times sine of pi over 4, which is square root 2 over 2. And this gets us square root 2 plus square root 2 times I. And now x1, we plug that in, and we'll end up getting the same 2 times, and now we'll have pi plus 2 pi, which is 3 pi over 4. And 3 pi over 4, cosine of 3 pi over 4 is negative square root 2 over 2 plus I times square root 2 over 2. The sine of 3 pi over 4 is square root 2 over 2. And this results in negative root 2 plus root 2I. And then we have x2 is equal to 2 times, and we'll get cosine of 5 pi over 4, which is negative root 2 over 2, plus I times negative root 2 over 2. And then to round this all out, we distribute and we get negative root 2 minus square root 2I. And x3 is equal to 2 times, and now we'll have cosine of pi plus 6 pi, so that's 7 pi over 4. So cosine of 7 pi over 4 is square root 2 over 2. Sine of pi over 4 is negative square root 2 over 2. So we have x3 is equal to square root 2 minus square root 2 times I. And there's our 4 roots of unity, in addition to, or our 4 roots of 16. Here are 4 roots of 1. Now, why did I choose pi? So again, we have a negative 16. So in order to find a negative 16 in terms of the representation, I needed to start here. That's where I needed to start, was at negative 16. And now I form my circle, and I'm starting on one part of the circle, and now I go around. So I had to think, how do I get to this negative 16? Well, we can think of this as 16, and now I'm going pi to get there. So that's why I'm using pi for my theta. If I don't have that pi, I'll get different roots, but I'm not going to get negative 16. I'm going to get 16. So in total, the solutions are 1, I, negative 1, negative I, square root 2 plus square root I, negative square root 2 plus square root I, negative square root 2 minus square root 2 times I, and square root 2 minus square root 2I. This was a longer video, but it's a lot of concepts, especially when we get to the general root theorem. The important aspect is that when we want to find this theta, we have to find it to our number that we're looking for. And typically it'll be a 0 or a pi. And if it's like the first example where we had 8i, we want to go to pi over 2, because that's how we get to the y-axis. That is all. Thank you for watching and have a great day.